Hi everyone, I'm Santipriya from Department of Mathematics and Statistics, Bhavan Vivekananda College. I'm here with my lesson 2 from Differential and Integral Calculus. In this lesson, I'm going to explain about first one is what is partial differentiation, second, functions of two variables, and then domain and range of functions of two variables, then neighborhood of a point a comma b, and then limit and continuity of a function of two variables, and lastly partial derivative, definition, and few problems on partial differentiation. So to start with, let us look at what is meaning of partial differentiation. Partial differentiation is used to differentiate mathematical functions having more than one variable in them. In ordinary differentiation, we find derivative with respect to one variable only, because a function of one variable will have only one independent variable. But in partial differentiation, we have to find derivatives with respect to more than one variable. What do we mean by that? Suppose, like when we recollect what is ordinary differentiation, when you have a function y is equal to f of x, that is y is a function of x, then we differentiated y with respect to x, that is we had dy by dx, that is d by dx of f of x. But suppose I have a function like this, z is equal to x square plus 2xy. So here I have z is equal to a function of x comma y. So there are two independent variables x and y and one dependent variable. Z is a function of more than one variable. Then in this case, what do you do? Do you find dz by dx? Do you differentiate z with respect to x? Or do you find dz by dy? That means, do you differentiate z with respect to y? What do you do? So there we get the case of partial differentiation. That means we can differentiate, we can find the derivative of z with respect to x, that we call, and as well as we can find the derivative of z with respect to y also. So that we call it as partial differentiation. So we can differentiate z partially with respect to x in one time, and the other time we can differentiate the same z with respect to y partially. That is what we mean by partial differentiation. So when we say partial differentiation is required when a function has more than one variable, first let us talk about what are functions of two variables. So here, if you take a function which is in the form of z is equal to f of xy. So here we can see there are two independent variables, x comma y independent variables, and z is dependent variable. So number of independent variables are 2. So this function is called function of two variables. Here we can see how does a graph of a function of two variables appear. So here if you take a function z is equal to f of xy. So there are two independent variables and one dependent variable. So totally variables are 3. But z is independent and xy are independent variables. So this will give us points order tried xyz in the xyz space, that is the three-dimensional space, and any function which is given in the form of z is equal to f of xy can take like this in a graph. So it can be a surface, it can be a curve, it can be like anything which is there in the three-dimensional space, xyz space. Here we can see few more graphs of function of two variables. You can check here different graphs. These are all functions of two variables. Totally three. Z is a function of f of xy. So total three variables, one dependent and two independent variables. So those type of functions will give us graphs in like this. These are the few examples. Now let us look at graphs of single variable versus two variables comparatively. So the left hand side one, whatever you have, it is a graph in two-dimensional plane, two-dimensional plane. then which is a circle here, x square plus y square is equal to 9, which you can write as y is equal to plus or minus under root of 9 minus x square. Y is equal to f of x. It is in two-dimensional space. Whereas if you take a function of three variables as shown in the diagram, the second diagram, z is equal to f of x y. Z is a function of x and y. There are two variables. So these two variables, and together with this variable z, it will give us curves or spaces in the three-dimensional space. Now let us come for the concept domain and range of functions of two variables. How you had domain and range for function of a single variable, in the same way for the functions of two variables also the same definition, meaning of the definition will be the same. So domain is the set of the points where we take the input, and a range is the set of all those points where you get the output. In general words you can understand like that. So if you observe this Venn diagram also here, so this is the domain. So the set of, so if you see the definition, the set of points xy where the function is defined is called a domain. It's domain. So if you just, if I say this is A, and then this is set of all those ordered pairs xy, because there are two variables xy, and then f is a function from the set A to B, where in B you had the image of x comma y is f of xy. So here A is called the domain and B is called actually codomain. In this, only the set of all those which are the images, this is called as the range. So, and the function is z is equal to f of x comma y. So this is already written here, domain, codomain and range. So you can see codomain means it will have all the elements in B, but which are the images which are mapped with xy, they will be in the range, set of all the f of xy. So here domain is A, so the set of points xy where the function f is defined, for what values the function is defined is called the domain. And whereas the range, if you compare, the range of the function is the set of its values f of xy, that means the images, or you can say output, for all x comma y in its domain, for whatever the values are there in the domain. So what is it defined for? Then the resulting, that is the output, set of all the output, that is called the range. After we defined about the domain and the range of a function, now let us look at few examples in finding domain of a function of two variables here we mean by. So for this I'll take the first example. Consider a function z is equal to square root of 1 minus x square minus y square. So here that is this is a function, you can compare it with z is equal to f of xy, and we know that here you have x comma y, to each x comma y, if f is a function, then you have here f of x comma y, each xy is related to f of x comma y. Now for us here we have, if this is x comma y, a point, and z is a function, then this z is given by under root of 1 minus x square minus y square. Now we have to find out domain. So here we have that for each x comma y, where is this x comma y? In xy plane, z is to be determined that z is equal to square root of 1 minus x square minus y square. So for us, finding domain for z is to find out the points x comma y for which square root of 1 minus x square minus y square is determined. So right? That implies we have square root 1 minus x square minus y square is determined. When can you have this value? If 1 minus x square minus y square is greater than or equal to 0. That implies I can write 1 is greater than or equal to x square plus y square, which implies x square plus y square is less than or equal to 1. What do you mean by that? For this function, for this z, it is determined for x square plus y square less than or equal to 1. Hence, domain of z is equal to square root 1 minus x square minus y square is the region x square plus y square less than or equal to 1 for x comma y. So this I will write it as, it is written as set containing all the points x comma y such that x square plus y square less than or equal to 1. Now let us see, we can even determine geometrically also, because here I can make it as a note. X square plus y square less than or equal to 1 gives a circular region with center at origin. I can say center at origin, radius equal to 1 in xy plane. So let us see what it is. If I take three-dimensional space, I will take three-dimensional space. Then where do I have xy plane? So this is negative x-axis, and this is negative y-axis. So what is x square plus y square less than or equal to 1? Here x square plus y square is equal to 1 is a circle. This is a circle. But what is circular region x square plus y square less than or equal to 1? This is a circle. I can say circle circumference. You can say this one. X square plus y square is equal to 1. Now what do you mean by x square plus y square less than or equal to 1? This circular region. This circular region is x square plus y square less than or equal to 1. All the points inside this circle will be the domain for the function. So, and even we will write this function as, the function is written as z is equal to f of x comma y, that is equal to under root of 1 minus x square minus y square, such that the domain is all the points xy such that x square plus y square less than or equal to 1. This is what we mean by finding domain of a function of two variables. Now let us look at the second example. So here you have, you are given the function. So find the domain of z is equal to under root of a minus x into x minus b plus under root of c minus y into y minus d. So let us look at the solution. So you are given this equation, let it be 1. Then finding domain for z implies finding region for x comma y to satisfy equation 1. So 1 implies I have, here you have 1 is sum of two under root functions. Under root of a minus x into x minus b is defined only when a minus x into x minus b is greater than or equal to 0. That is, if I take minus common, minus of x minus a into x minus b greater than or equal to 0, which implies x minus ba into x minus b is less than or equal to 0. And if you have remembered, this implies in quadratic equations you have learned when x minus a into x minus b less than or equal to 0, then you will have x lying between a and b. This you learned in intermediate. So similarly, I can say under root, what is the other term? You c minus y into y minus d is defined only when c minus y into c minus y into y minus d is greater than or equal to 0. That implies minus of y minus c into y minus d is greater than or equal to 0, which implies y minus c into y minus d is less than or equal to 0. As in the above case, this is also satisfied when y lies between c and d. Now let me take this as 2 and this as 3. Therefore, from 2 and 3, x comma y from 2 and 3, let me make it correct, from 2 and 3, point x comma y satisfies the region, or I can say instead satisfies, I say lies in the region where a less than or equal to x less than or equal to b and c less than or equal to y less than or equal to d. What does it give us? That it gives us this implies, I can say this implies a less than or equal to x implies x is greater than or equal to a, and x is less than or equal to b implies x is less than or equal to b. That means if I have like this xy plane, if this is x-axis, suppose what do you mean by x is greater than or equal to a? So that is x is equal to a. Suppose a is here, this is a value, it gives you x is greater than or equal to a. And here you are given in the question, it is given that what about it is assumed, I just forgot to write here this one, it is understood that a less than b not equal to, it is given in the question, and c is less than d. So if I come till here, if this is b, then x is greater than or equal to a, and this one is x is less than or equal to b. So that means this will give you this Similarly, C less than or equal to Y implies Y is greater than or equal to C, and here you are given A less than B, and you are given even C is less than D. Where is C here? If this is C and if this is B, then Y is greater than or equal to C, so that means it will be there here. And then Y is less than or equal to D. Y is less than or equal to D. If this is D, so what is the common region? This is the rectangular region. You can say if this is A and this is B, this is C and this is D, then in this area you will have A less than or equal to X less than or equal to B and C less than or equal to Y less than or equal to D. Hence, the domain is a rectangular region bounded by X is equal to A, X is equal to B, this is X is equal to A and this is X is equal to B, and Y is equal to C, this is Y is equal to C, and Y is equal to D, this is Y is equal to D. So this is X is equal to A line and this is X is equal to B line, this is Y is equal to C line and this is Y is equal to D. And we'll write it as domain is set containing X comma Y such that A less than or equal to X less than or equal to B and C less than or equal to Y less than or equal to, this is a domain. Now let us look at the third example. Example 3. Find domain of Z is equal to e power minus x square minus y square. Solution. So you have considered this equation Z is equal to e power minus x square minus y square. Just recollect, Z is equal to e power x is defined for all real x, that is for all x belong to R. For all the real numbers this is defined. Now let us look here for this problem what we have. Now e power minus x square minus y square is defined for all x comma y, or I can say for minus x square minus y square belong to R. Then I can say minus x square minus y square belong to R for all x comma y belong to for all x comma y I can say, right. That implies minus x square minus y square belong to R for all points x comma y in xy plane, or for all ordered pairs of real numbers x comma y. Therefore, what is the domain? Hence, domain is equal to set containing x comma y such that x belong to R, y belong to R. All the entire xy plane, that is entire xy plane is the domain, right? So that means finding domain means for what values of xy it is defined. Now let us look at the another problem. Next example. That is, we are given here, find domain of the function f of xy is equal to 1 by log x plus log y. Right. Now here you have to, let us look at solution to find domain of f of xy is equal to 1 by log x plus log y. This is 1. Implies to find for what values of x comma y, 1 by, for what values of x comma y, 1 by log x plus log y is defined. Now here you can observe this function. It is first a reciprocal function. So when you have 1 by x is defined when x not equal to 0. So the first point here is defined, that is number 1, first point, log x plus log y should not be equal to 0. And again, here logarithmic functions are there. So second point is log x is defined for all x greater than 0. So the second point is for x greater than 0, and log y is defined for y greater than 0. So let us look at one by one point. This one implies log x plus log y, log x must not be equal to, implies not be equal to minus log y. So which is possible for all x comma y. For any x comma y, you will not have log x equal to minus log y. It will never happen. So log x is not equal to minus log y, which is possible for all x comma y. So this is therefore log x plus log y is not equal to 0 for all x comma y in R, I can say. And the second point is already this implies already we have x greater than 0, y greater than 0. So by observing this, therefore domain is equal to set containing all x comma y such that x greater than 0, y greater than 0. So what will the geometric or graphical representation if I take xy plane? I am only showing in 2 dimensions. This is xy plane. All x greater than 0, y greater than 0, where will they be? In the first quadrant. X should not be equal to 0. That means it cannot be on the, it shouldn't be on the x-axis, it shouldn't be on the y-axis, it should not be at the origin also. It should be only in the first quadrant. So this is the domain for the function. So the same thing you can view in 3 dimensions. I can say in 3D, this is xy plane, but xy plane I can see this is negative x-axis, negative y-axis. Then where is both positive? This is the both x and y are positive, infinitely it will go. This will be domain. So basing on this, you can work out some other problems also. Here are few practice problems for finding the domains of the functions of two variables. Let us try to understand now neighborhood of a point a comma b. In the introductory lesson, I explained about neighborhood of a point a on a number line. That is when we have taken a number line, a real number line, and if you consider a point, I will take with example only, suppose 2, and then I will take epsilon is equal to 0.01. So I'll get here 2 plus epsilon means 2.01. So this is 2.01, and 2 minus epsilon means 1.99. So you have 1.99. So all those real numbers which lie between 1.99 and 2.01, they will come under the neighborhood of 2 with radius epsilon is equal to 0.01. Like that, for any real number, you can write its neighborhood. Now what about neighborhood of a point which is in the form of an ordered pair a comma b, because we are going to deal with functions of two variables. So two variables, if I take x comma y, so they are represented by ordered pair x comma y. So we need to now talk about neighborhood of a point which is in the form of a comma b. For this, what do? I'll take, since I have to find the neighborhood of a point AB which has two variables, I'll take two-dimensional plane. I'll take a two-dimensional plane, xy plane, and then on this, let me take here x on the, this is origin, and then suppose I need to now, I'm taking here A. So this is, if I have here A and then here I have B, then I will take delta. For A, I will take a smallest positive real number delta. Instead epsilon, I will take delta. So this is A minus delta and this is A plus delta. So I have between A minus delta and A plus delta, and then I have I'll take for B also, I'll take from B minus delta to B plus delta. So this is B minus delta to B plus delta. Then what are all those points which lie between? So x should lie from A minus delta to A plus delta. So where will x be? Here it will be. And y should lie between B minus delta and B plus delta. So where then the resultant values will be in this rectangle. So the point A comma B, this is the point A comma B, P A comma B. This point will lie in this rectangular region. So the neighborhood of this point P A comma B will be a rectangular region. So which will be having where A is lying in the interval A minus delta to A plus delta, and B is lying in the interval B minus delta to B plus delta. That is what here the definition also says. So let delta be any positive number, least positive number we will consider, like epsilon. Then the points xy such that where x lies between A minus delta and A plus delta, that is A minus delta less than or equal to x less than or equal to A plus delta, comma y lies between B minus delta and B plus delta. So B minus delta less than or equal to y less than or equal to B plus delta. This determine a rectangular region bounded by the lines. What are those lines? This line is, whatever this line is, x is equal to A minus delta, and this line is x is equal to A plus delta, and next one, this line is y is equal to B minus delta, and this is y is equal to B plus delta. So the region which lies in this rectangular region that is called as the neighborhood of point A comma B. Now let us look at what do we mean by and what do we define as limit of a function of two variables. Before defining, let us look at it with a small example. Suppose like I'll explain this concept with the domain and codomain concept only. Suppose I have the point x comma y here, and I have then obviously if the f is a function from a to b any set, then f of xy will be here, and this f of xy, suppose xy is reaching another point a comma b. So what do we mean by f of xy is reaching a comma b? The distance between xy and ab is reducing. How do you denote the distance? Distance we'll denote with the modulus value. Distance between the points x comma y and a comma b is reducing. When it is reducing, we'll say that it is less than delta. Delta is the least positive integer. If there is anything which is less than this delta or epsilon, whatever we take, that will be nothing but 0. So in mathematics, if I say the distance between any two values, if I say modulus x minus a less than delta, what do I mean by that? X is tending to a. You can say x is tending to a, or you can say the distance between x and a is reducing. It is almost 0 but not 0. So that concept we will use with the modulus x minus a less than delta. That modulus and this least positive integer values, we will least positive real numbers values we will use here. Then when I have here xy is reaching a comma b in the domain, then in the codomain you have here f of xy, then f of xy also, then this a comma b also will be having some image, or you can say here f of xy will be reaching, suppose it is reaching a value L. That means the distance between f of xy and L is reducing. So modulus of f of xy minus L is also less than epsilon, less than another positive, least positive real number. That means f of xy is reaching L, then you call this L to be limit of the function f of xy. So I hope this like explanation is clear. Now let us look at the words that are written in the definition. A function f is said to tend to the limit L as xy tends to ab. What do you mean by xy tends to ab? In the domain, the point xy and ab, the distance between xy is a variable. So it keeps on changing the value. So if you give values, different values, so that this xy value reaches a comma b, if corresponding to any pre-assigned positive number epsilon, that means epsilon is any positive real number, then there exists a positive number delta such that modulus xy minus ab less than delta, that is the distance between xy and ab is reducing, implies modulus of f of xy minus L is less than epsilon, the distance between f of xy and L is reducing. And it is written as limit of f of xy is equal to L as x comma y tending to a comma b. After completing the definition of a limit, now let us look at its extension, that is continuity of a function of two variables. So before starting this continuity definition, I'll just again recollect whatever we defined in the previous limit. In the limit we defined that if x comma y tending to a comma b, then f of xy, its image f of xy, if it is tending to L, some limit value L, then you call limit of f of xy is equal to L, right? Now you observe the same thing even in the definition of continuity I used. If in the domain x comma y is reaching a comma b, then f of xy is reaching f of a comma b. See here I wrote L, but even you will have here image for f of this one also. As xy has f of xy as its image, ab also will have f of ab image in f, since f is a function. Then this f of ab is equal to L, the limit whatever we were talking in the limit. If this limit itself is the image, f of AB, then you call that function to be a continuous function. So let me draw again and make it more clear. So you can understand here in the domain f of xy is there, so f of xy is there. AB is there, then f of AB is also there. Then if x comma y is tending to a comma b, then if as x comma y tend to a comma b, f of xy also tends to f of ab and none other than f of ab. This itself, if it is the limit L, then you call this function f to be a continuous function. So here you can at a point, at a given point. So let a comma b be a point in the domain of the function z is equal to f of xy. And if for the points xy near AB, so nearest points only we'll take, then the value of f of xy of the function, if it is near to f of AB. And what do you mean by near AB? Means xy is reaching AB, then f of xy is reaching f of AB. That is xy is reaching f of AB implies f of xy is reaching f of AB. Then we say that the function f is continuous at a point AB, f is nothing but z is equal to f of xy. So function of two variables z is equal to f of xy is continuous at a point AB if I can say, even I can write this as limit of f of x comma y as x comma y tends to a comma b is nothing but f of a comma b. In limit before we wrote it as it can be some other value L. Now if it has to be continuous means that L is nothing but f of AB only. If that is satisfied, then we call that function f to be a continuous function. Now let us come for the definition of partial derivative. Before defining partial derivative, let us recollect once what is the definition of derivative, ordinary derivative. So just recollect the concept that I taught in the previous lesson. So if you have a function y which is a function of single variable y is equal to f of x, then we had differentiation dy by dx, that is differentiating the function y with respect to x, and the definition what we had is it is limit of f of x plus h minus f of x by h as h tends to 0, where the function is given as f of y is equal to f of x. Now we are taking the function of two variables. So how will be the function? The function is in the form of z is equal to f of xy. So wherever you have taken f of x, we should take now f of x comma y. So here consider z is equal to f of xy. Then partial derivative. So when I say partial derivative, that means it's not a complete derivative. Since there are two variables x and y, we can differentiate the function z with respect to x. So, and next in the next case, you can differentiate the same thing with respect to y, not at the same time with respect to both the points. So the first, if I take, suppose we are differentiating the function z with respect to x, then partial derivative of f with respect to x, we call it as, and it is denoted by dou z by dou x. Dou, it is not a d. For ordinary derivative, we will use d by dx. Ordinary derivative, we will use d by dx, and for the partial derivative, we will use dou by dou x. So dou by dou x of the function z. So that is dou z by dou x. So you will denote it as f of derivative of f of xy. Here you will write this subscript x, fx of x comma y. Then it is the same as limit, how you have defined for the definition of ordinary derivative. Limit of what is that function? F of xy, and there is, you are differentiating with respect to x. That means there is a change in only x. Y is considered as a constant. There is no change in y. So there is no change here. So you have written f of x plus h comma y minus f of xy by what is that change in the x value h, as h tends to 0. This is defined. This is said to be as the partial derivative of f with respect to x. Similarly, we can differentiate the same function z is equal to f of xy with respect to y. In that case, we don't change anything x. So here you have partial derivative of f with respect to y. You will denote it with dou z by dou y, and you will write it as fyxy. Fy, the function f of xy is differentiated with respect to y partially, is equal to limit of, now f of, in x and y the change should be only in y, not in x. X is treated as constant, so keep x as it is. So what is the change you are taking in y? K. So x comma y plus k minus f of xy. So that is the difference in the change f value. F of then divided by k, that whatever the change, then as k tends to 0, then this ratio is said to be the partial derivative of f with respect to y. Now I'll talk about partial derivatives at a given point a comma b. Actually we have to learn first at a point differentiation, and then the partial derivative for the entire domain. But to understand it, it is better to first learn what is partial derivative, and then to go try understanding partial derivative at a point a comma b. So the same concept. So consider here a function z is equal to f of x comma y, and then at a point a comma b I am measuring the partial derivative. So in place of x I will write a, in place of y I will write b, and it is the definition is the same. So it is, if limit of f of, instead of x plus h I am writing a plus h comma, in place of y b minus f of a b by h as h tends to 0. It is said to be the partial derivative of the function f with respect to x at a point a comma b. It is denoted by fx of a comma b, or you will say it is dou z by dou x at the point a comma b. So the similar way, partial derivative of f with respect to y at the point a comma b will be, if the limit f of a comma, there is no change in x, so you are differentiating with respect to y, so there is no change in the x coordinate, so x is equal to a will remain as it is, and there is a change in y place, that is it is changing at k, and at y means here you have taken b plus k, f of a comma b plus k minus f of a comma b by k as k tends to 0. If this limit exists, then it is said to be the partial derivative of f with respect to y at a point a comma b, and it is denoted by fy a comma b, or you will write it as dou z by dou y. Derivative of z, partial derivative of z with respect to y at a given point a comma b. Like this, in the domain at every point a comma b, if the function is differentiable, derivable, then we call that function to be derivable on the entire domain. Now let us do the partial differentiation for given functions of two variables. So here the first one is finding dou z by dou x. So what do we mean by that? If a function is given z is equal to f of x comma y, so first we have to find out dou z by dou x, or you call it as fx. What do you mean by that? When you are differentiating z with respect to x, then treat y as a constant. Other than x, whatever you get, that is a constant. So here y is a constant. So how you treat constant when you are differentiating? The same way. So let us look here. Now what do we mean by dou z by dou x here? So dou z by dou x means differentiating z is equal to f of xy with respect to x, treating y as a constant. So example, z is equal to x square plus y square plus 2xy. Then differentiate z partially with respect to x, that is treating y as a constant. Dou z by dou x is equal to dou by dou x of x square plus y square plus 2xy. Now, like the same differentiation rules what you have learned earlier, you can write it as dou by dou x of x square plus dou by dou x of y square plus dou by dou x of 2xy. So let us see dou by dou x of x square, dou by dou x of y square, and dou by dou x of 2xy. So dou by dou x of x square, you are differentiating x square with respect to x. So x power n formula, dou by dou x of x square is equal to 2 into x to the power of 2 minus 1. So which is equal to 2x. That is done. Then the next term is dou by dou z of y square. Dou by dou z of y square. Just we have written here, treat y as a constant. What is the derivative of a constant? Dou by, sorry, this is dou x of, dou by dou x of y square, right? So you are differentiating with respect to x, but you are differentiating y square, so it will be treated as a constant. So what will be dou by dou x of y square is 0. So this is 0. And the next one is, you have the next term, dou by dou x of 2xy. Dou by dou x of 2xy. So this is dou by dou x of 2xy. In this, only x is a variable and the other terms 2 and y are constant. So any constant you can bring it out. 2y into dou by dou x of x. 2y is a constant, y is also a constant. 2y into dou by dou x of x. Dou by dou x of x is 1, so 2y into 1 will be 2y. So you have, this is 2y into dou by dou x of x, which is 2y into 1. So it is, final answer is 2x plus 2y. Next, let us look at dou z by dou y. So dou z by dou y means differentiating z with respect to y and treating x as a constant. So z is equal to f of x by function is given to us, that we will find dou z by dou y, that is treating x as a constant. So dou z by dou y, or you can write it as fy. So that is differentiating z with respect to y, treating x other than any element other than y as a constant. Now I have taken the same function. So z is equal to x square plus y square, x square plus y cube I have taken here, okay. X square plus y cube plus 2xy. So then differentiate z partially with respect to y. That is treating x as a constant. So you have dou by dou y is equal to, dou z by dou y is equal to dou by dou y of x cube plus y cube plus 2xy, which is equal to x square, sorry. Then this is dou, and again apply this dou by dou y of x square plus dou by dou y of y cube plus dou by dou y of 2xy. So it is dou by dou y of x square plus dou by dou y of y cube plus dou by dou y of 2xy. So when it comes for the dou by dou y of y x square, dou by dou y of x square, you are differentiating with respect to x y, and the variable is x. So this is a constant, so it is 0. Because other than y, anything is treated as a constant. Next one is dou by dou y of y cube. Dou by dou y of y cube. So this is, you are differentiating with respect to y and the function is in terms of y. So it is 3 into y power 2 minus 3 minus 1, 3y square. That is clear. And the next last term is dou by dou z, dou by dou y of 2xy. Dou by dou y of 2xy. So in this y is only variable, other 2 and x both are constant. So you can write it as 2x into dou by dou y of y, which is equal to 2x into, what is dou by dou y of y is 1, so it is 2x. 2x into 1 is 2x. So finally the answer is 3y square plus 2x. Now let us quickly look at the same previous problem together, that is dou z by dou x versus dou z by dou y. So here the z is equal to the function taken as x square plus y square plus 2xy. The second one I have taken z as x square plus y cube plus 2xy. So when I am differentiating dou z by dou x, so I have taken differentiating x with respect to x, treating y as constant, whereas when you are differentiating z with respect to y, treat x as a constant. That point always you have to remember. So dou z by dou x is equal to here dou z by dou x of all this, dou z by dou x of x square plus dou z by dou y of dou x of y square plus dou z by dou x of 2xy. Dou z by dou x of 2x square is 2x, and dou z by dou x of y square is 0, and dou by dou x of 2xy is 2y into dou by dou x of x. That is equal to dou by dou x of x is 1. And similarly, you can check here the same function, little bit y power is different. That's it. So dou z by dou y is equal to dou by dou y of x square plus dou by dou y of y cube plus dou by dou y of 2xy. Same thing. Dou by dou y of x square is 0 and dou by dou y of y cube. It is y cube with respect to y you are differentiating. So 3y square and dou by dou y of 2xy is 2x you will bring it out and dou by dou y of y is equal to 1. So you have here 3y square plus 2x.